So, hello, I'm Sylvain Bouillon. I'm from the NERSC Center in Bergen, Norway. I'm part of the sea ice modeling group that is led by Pierre Rampal. And the work I'll present has been made by me and my colleagues. So this is sea ice. It's a picture taken north of the Canadian Arctic archipelago, so it's in the Arctic. On the far end, you see the land covered by ice and snow. Then there is a band of land-fast ice. It's sea ice that is attached to the coast or grounded, so it's touching the sea bottom. Then there is this band of open water, which is what we call a polynya. That's very important for many processes. Then over here you have a band of thin ice, so it's sea ice that is very thin, like a few centimeters. And then there is the ice pack. So this part, it's only a small portion of the ice pack. It's moving ice that is typically 1 or 2 meters thick. So the presence of sea ice is very important for ocean-atmosphere interaction because, for example, if you have sea ice, you will have a very high surface albedo. So it means that most of the incoming radiation will be just sent back to space, or to the atmosphere at least. The surface albedo is a bit lower if you have thin ice, and it's much lower for the open water. It also has a large impact on the heat fluxes. So the heat fluxes are much stronger over open water than through the thin ice or through the thick ice. So there are also other important processes affected by the presence of sea ice. For example, the momentum fluxes, but also the fact that when we form sea ice, there is a large portion of the salt that is rejected directly to the water. So it's important to understand and simulate the sea ice state, but the sea ice state can change very quickly due to sea ice dynamics. And to illustrate that, I'll show you an animation taken from or built from satellite images. Here, the image covers the Beaufort Sea, so it's still in the Arctic. We have the Canadian archipelago over here, at least a small portion of it. And here there is Bering Strait and Point Barrow. So Alaska over here, and the Canadian Arctic archipelago over there. On the image, what you can see, you have areas that are very dark. It's the ocean. Then the gray zone, the gray color, it's the sea ice. For example, here we have a polynya, as in the picture I just showed. It's a big coastal polynya. We also see fractures. All these small lines are fractures. We also call them leads. So it's a fracture in the ice. And the animation is for 2 months, and it's showing a large breaking event that took place in February, March 2013. So at the beginning, only the left part of the domain is moving. You see a lot of blocks that we call flows that are formed over here and that are drifting towards Bering Strait. You see also large fractures and leads formed on the left-hand side, but the right-hand side is not moving. It's almost static. And then at the beginning of March, there is a storm passing over the region, and it actually completely breaks the whole ice pack over this very large region. So the dynamics of sea ice is completely different from before and after the storm. You have all these big blocks that can be hundreds of kilometers large that are formed. There is also over here along the coast a very long coastal polynya. So you can imagine the change in terms of interaction between the ocean below and the atmosphere caused by just this specific storm. So sea ice dynamics, it's important for understanding sea ice state and how it evolves. but it may also directly affect the ocean. So this is an example. It's the speed, the sea ice speed observed from satellite. And what we see is that it's a discontinuous field. So here we have one plate moving with a specific speed, and then there is another plate just along the first one, with moving with another speed. And the two, these two ones are moving one along the other. So there is a strong shear at the surface of the ocean due to the discontinuity in the sea ice motion. And this is a specific example because there was a scientific campaign that was located exactly at that location during this strong shear event. And what they were measuring is the salinity temperature below the sea ice. And what they observed is actually during this strong shear event, they found that there was a strong increase in salt and temperature just below the sea ice. And this is due to the upwelling of the pycnocline. So there is a strong shear caused, there is a strong shear in the sea ice deformation that is causing localized shear stress, and that is creating this upwelling of the pycnocline. So this is a very important mechanism that is not yet fully understood and not well simulated. So that was for the motivation. Why is it important to understand and simulate sea ice dynamics? But it's only one part of the story, because it's also a new frontier for oceanography and polar oceanography. And it's a new frontier for three reasons. The first one is that the sea ice modeling, and especially sea ice dynamics, it's quite new compared to what we know about the ocean and the atmosphere. So for example, we don't have the fundamental equations for sea ice dynamics. There is no equivalent of the Navier-Stokes equation for the sea ice. Then the second reason is that the properties, the material properties of the sea ice are very specific and explain a large part of the nonlinear and complex behavior of the ice pack. And then the third reason is that it's only recently that people have looked at mesoscale sea ice dynamical features. So for the atmosphere, we have the synoptic features that have been studied a lot. In the ocean, we have the eddies, and the equivalent in the sea ice are those linear kinematic features, or the fractures and the leads. So it's new, and that's what I want to discuss today with you. So this presentation is complementary to what we put in the book. So instead of having, so if you like equation, read the book, or the chapter, and if you like animation, then you will like this presentation, I hope. So let's start with sea ice material properties. So it's really easy. You can do it in your kitchen. You just take an ice cube from the freezer. You will directly see that it's a solid. It's not a fluid. It's brittle. So if you try to push it, it will not deform. And then if you push stronger, it will break. And it floats. So that's basically all you need to know about the material properties of the sea ice, at least to start, as a start. So if you want to have more information and if you want to understand sea ice dynamics, you need to go on the field. And then you will see it's quite a dangerous place, because you have, it's very heterogeneous, the landscape on the sea ice. You have, for example, these pressure ridges that can be several meters thick. So it's very complicated to travel across or on top of sea ice. To have a better idea of how it is complicated, you can use instruments to, for example, to measure the sea ice thickness along a track. And so the first important information about that is that there is a very large aspect ratio. So the sea ice thickness is typically 1 or 2 meters, whereas it extends over thousands of kilometers. So it's basically a 2D media. And it's highly heterogeneous, but you can very well describe the sea ice heterogeneity by looking at the ice thickness distribution. For example, in this picture, we have a lead with thin ice in it. So this is the first mode of the distribution. Then we have the level ice, which is the undeformed ice. So it's more or less the equivalent to the mean value of the sea ice thickness. It's the second mode of the distribution. And then you have all this, what we call the keel and the ridges that are explaining the tail of the distribution. So it's more or less always the same. If you just travel in the Arctic, you compute the ice thickness distribution, ITD, and what you got, it's almost always a first mode for the thin ice, then a second mode for the level ice, and then the extreme values corresponding to the ridges. So it's very important to know this ice thickness distribution if you want to compute the fluxes through the leads, if you want to have a good approximation of the many processes acting near the sea ice. The ice thickness distribution, so the presence of leads and ridges, are mainly controlled by localized deformation events. So it means that, so if you are on the field, again, with your camp on the sea ice, what can happen is, for example, that you have a big lead just appearing in a matter of hours in the middle of the camp. So that can be quite complicated for logistics afterwards. So this is caused by strong localization of the deformation, or this is caused by discontinuities in the sea ice motion, either in shear, divergence, or convergence when you close the lead. And then you can also have ridging, so that's when you have strong convergence or ridging, and you can create these pressure ridges in a matter of a few hours. So to have a better understanding, it's not enough to just go on the field. You need to go, or at least to use information from space. And those information have been available from the 90s from SAR images. So there are satellites taking picture of the sea ice, even if there is no one over there. And from these high-resolution SAR images, what you can do is to identify points on the image and to track, for example, here, if you look at this flow, you will find it in the second image and in the third image. So you can track points, virtual points. And from that, if you do it for many points, for example, all the nodes in this array, you can you can compute the drift of the ice, but also the deformation, so the large-scale deformation. For example, for this cell, you see that it has been opened, so it has a larger area than the original cell. So it means we had divergence over here. And that one has been deformed with no change in the area, so we had shear. So this cell or this region has been sheared. When you do that on a very large scale, so if you do that for the whole Arctic or for the whole for the central part of the Arctic, that's what you get. So this is the divergence field. It's red when you open, blue when you close. So for example, here we are opening what could be a large lead. You can also compute the vorticity, so just how it rotates, and the shear rate, how it's shearing. And what is obvious is that, so we have a strong localization in space, so of the deformation, and this is related to discontinuities in the sea ice motion. So you have the sea ice motion, the x and y component of the sea ice motion, and the large value of deformation are caused by discontinuities in the sea ice motion. And what is also interesting to see is that when they are formed, these what we call linear kinematic features, they are aligned with the isobar. So it's mainly the atmosphere that is driving or causing this deformation. So this is the same information, just from another example. You take two images, you compute the drift. This is the first level product from the satellite. And once you have the drift for many points, you can compute the deformation. So this is an example of a deformation field. It will be an animation for the full winter. At the beginning, we only have a few satellite tracks, but then it rapidly covers all the region. So what you see is that it's strongly localized in space. We have these linear features, but the way they evolve is also very, so there is also a strong localization in time. So you have linear features that are active a few days and then they are not active anymore. So it's also very localized in time. And this is quite unique in geophysics, at least compared to the ocean and the atmosphere. So how do we do to quantify this localization? What we do, we compute the velocity gradient at the resolution of the data. So for example, at 7 kilometers. Then we do the same at coarser and coarser resolution. And from the velocity gradient, we compute the shear and the divergence. So this is, for example, the shear. And what is important to note is that even at 100 kilometers, the deformation is still highly localized. So it's not noise. That would be almost zero at much larger scales. So we have to take that into account. And we can do the same in time. So if you just take two buoys or 2 points in the sea ice that has an initial separation of 10 kilometers, and then you follow how the separation evolves in time up, you will have this localization of the separation rate in time. So this is the separation rate in kilometers per day. So here we can identify two events where the separation strongly increase in a matter of a few days. So deformation is also strongly localized in time. So that was for the sea ice dynamics we can observe from in situ or from satellites. But now, how can we simulate that? When I started studying sea ice, it was a few years ago, there was only two types of models. There was either continuous Eulean, classical continuous Eulean model. So you have a fixed grid. And the problem with these models is that they have a very smooth representation of the sea ice dynamics. So basically, you don't see any discontinuities. So it's very smooth. Even if you run them at very high resolution, like a 10 kilometer, you will still get smooth velocity fields. And all the rest, all the effect of the deformation is largely parameterized. There was a second type of model. It's the discrete models. So we saw in the first animation that sea ice was composed of many blocks. So with discrete models, you simulate each blocks individually, and then they can collide, they can merge, they can be broken up. But the problem with this type of models is that you need to run at a very high temporal and spatial resolution, and it's maybe not fitted to do simulation over the whole Arctic, especially if you want to do climate type simulation. So that was the two options at the beginning of my thesis. So what I did with colleagues is to propose another approach, which is to build models that are able to localize at their nominal resolution. So it means that we have discontinuities in the simulated sea ice velocity. And it means also that we can check if we reproduce well the deformation from the resolution of the model to much larger scales. And of course, for the rest, for everything that is subgrid, for all the subgrid scales, we will still need parametrization, but at least we want to have everything good for the scales that are larger than the resolution. So that was a big challenge. So to do it, we asked help from other research field, and we had interaction with people doing solid mechanics because they had the same type of behavior with strong localization of the deformation. When you take a rock, you press it, it will break, a bit like the sea ice. So the concept we propose is to add a new variable in sea ice models that is called the damage. So it's the sea ice damage. And this is a small example. At the beginning, we start with an intact material. So it's like a big plate of sea ice with no damage. Blue is for the water, or for the water. And here we have the coast. If we push it, or if we apply a wind stress towards the coast, the internal stress will increase. And what happens with the with our model is that when you reach a given criterion, you increase the damage. And if you increase the damage in some cells, it means that they will resist less, so the internal stress will be redistributed around on the other elements, and they will start to break. And due to the interaction between all the elements, you will have a fracture that will emerge automatically from from running the progressive damage. So we end up with a brittle behavior. That's what we wanted. So it's a very simple model with just one additional variable compared to classical sea ice models. So when we run this type of model over on a realistic setup, so for example here, it's a setup covering the Kara Sea and the Barents Sea. So you have Greenland, Spitsbergen, Russia is over here. So this is the setup we used with realistic winds and so on. And that's what we get for the vorticity, the vorticity. We had typically 3 regions. The first one with big plates that are hundreds of kilometers, a bit like after the strong breaking event I just showed. Then in the Kara Sea, we have linear features because it's an enclosed or almost enclosed basin. So it's another type of physics at large scale. And then close to the open water, so this is the open ocean, and between the ice pack and the open ocean, we found a region with many small pieces. So all the ice is almost damaged in this region. And this is very similar to what we observed when we go in this marginal ice zone region. So that was the first type of results we got a few years ago. So to continue, we had to add the thermodynamics because sea ice melts and is formed by freezing. So we have a simple model with only 3 categories. So instead of representing the whole ice thickness distribution, we only have one value for the thick ice one value for the thin ice and one value for the open water for each cell of the model. And it's a very simple thermodynamic model with no heat content. It's maybe a bit too simplistic even. And then, so we add the thermodynamics and we implement a new type of numerical scheme to solve and to run the model, because we wanted to use a fully Lagrangian approach. And the reason for that is because the model is able to reproduce discontinuities. It means that we will have sharp gradient in the simulated field, and they will be localized at the scale of the model. So if you use a classical Eulerian advection scheme, it could be highly diffused because of numerical diffusion. So instead of that, we use a fully Lagrangian scheme. So with the mesh, the elements of the model are moving with the sea ice. So it's like if you just go on the field and you follow the sea ice. Because of that, we need to use unstructured grid, like that one. And we had also to implement the adaptation. So we have an adaptive mesh. So it means that when one of the cell is too deformed, then we will automatically remesh or adapt the shape of the cell. And to discretize in space, we use the finite element method. So we basically have the CI thickness, concentration, and damage centered in the triangles and the velocity vectors that are on the nodes. So this is an illustration of the conservation during a remeshing. So for example, here we had the old mesh in green, but it was too deformed, so we had to adapt the mesh, and that was done by forming these new triangles in red. And then we just transfer information from the old mesh to the new one with a conservative mapping that is done in an efficient way. This is another example. So thanks to that, we were able to use a fully Lagrangian advection scheme. And I will just show here a test case with a very strong gradient in the concentration, in the sea ice concentration field. There is no ice below this limit, and there is 100% ice in this part of the domain. It's a closed basin, and we just apply wind stress to the south. So at the beginning, nothing happened because we are attached to the coast. And then these blocks detach, and it's moving. It's moved south, and then it's touching the lower boundary. It's going to the left because Coriolis is still active in this setup. So what is nice with the advection scheme we have is that we keep the very strong gradient even if we have a very large advection of the field. So that was for a test case. Now if we just look at what it gives for a realistic case, so this is just a zoom over the Fram Strait, which is between Greenland and Spitsbergen. So it's coming from a simulation that ran over the whole Arctic domain. I think it was at 7 kilometer resolution. And this is the mesh. So you see all the triangles. The background field, it's the concentration. So there is no ice here, but there is still triangles, but you can't see them. So the model is still continuous. And what happens is that we have this strong localization, so discontinuities in the sea ice motion. So it means that the sea ice concentration drops because we open, so we increase the area of the triangles. when the triangles are too deformed, they are adapted. For example, here, you can see there are a lot of adaptation steps, and all is done automatically during the simulation. So it's quite nice. We have what we call arches, which are those lines of a very low thickness connecting the Greenland and Spitsbergen. So it looks very much like observations. So now when we to validate this type of model, what we do is first a long simulation, looking at the evolution of the sea ice concentration and sea ice thickness, starting from initial conditions that are taken from a classical sea ice model. So it's taken from the Topaz reanalysis. So what we have for initial condition, it's very smooth field with no discontinuities. We apply forcings from the wind. There is no ocean below, so it's a standalone simulation. And what we get very quickly, it's all these discontinuities, all these fractures, leads in the sea ice concentration. We have big blocks formed by the model and that are advected through Fram Strait. So it's very completely different from what you will get with a classical sea ice model. And this is caused by the fact that the sea ice motion is highly discontinuous. So if I just stop the animation somewhere, no, I will just wait. So you see, it's the sea ice velocity field is highly discontinuous. We have very strong gradient. So for example, here we have gradients in the velocity field. Here also, this ice is not moving, and just next to that one, we have a big piece of ice that is moving with a quite high speed. So if you have discontinuity in the sea ice motion, it means that you have localized deformation. So everywhere there is a discontinuity, there is strong values or large values of the shear and divergence. And that's what we wanted to simulate and to compare to observation. So this is the simulated fields as if they were observed from space. So we use exactly the same location, the same time periods that was used to get that field from observation, and we apply exactly the same process to compute the deformation from the model at the same location and the same time period. So it looks similar, at least qualitatively. If we just zoom in, we see that in the model we have this strong localized deformation bands, like in the observation. It's a bit more noisy in the observation than in the model. And then to have a better understanding of the differences between the observation and the model, what we do is this scaling analysis. So we compute the deformation at different scales, and what we look at is the statistics. So we compute the mean value at 7, 16, 30, blah, 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 up to 200 kilometers. And from observation, we know that the mean value of the deformation decrease as a power law, so it's a log-log scale. It decreases as a power law to the scale of observation. If it was a completely noisy field with no organization, no spatial organization, you would get a much stronger slope. So having a weak slope means that even at very large spatial scale, it's still highly localized. And we got the same for the model. So even at large scale, the deformation is still highly localized. And we do that not only for the mean, but also for the variance, for the second moment order and other moment order. And what is important is that if you compute the slope for different moment order, it will give you a quadratic function. So the slope is a quadratic function of the moment order. If you compute exactly the same, just taking a free drift is just you put buoys that are just moving with the atmospheric forcing, what you will get is a line. You will not get this what we call multifractal property, so the fact that it's quadratic. And that was shown in papers. So instead of just doing that for one snapshot, we do that for a whole winter here. And we look at the scaling, so how the mean, variance, and skewness depends to the scale. But we also look at distribution. So this is in a log-log plot, and this is in a semi-log plot. So here we got a linear tail in the log-log plot. So it means that the distribution of the deformation rate is a power law. Or at least it has a power law tail. So when we do that for the whole winter, we see that there are some variation of the intensity of the deformation. And this is caused by storms and wind changing over the domain. What is nice is that for all the snapshots, or for many snapshots, we get a good correlation of the statistics and the relationship and the right relationship with the scale. So we are quite happy with this type of comparison. So now that we have validated the deformation simulated by the model, we can just look at what gives the model by comparing the. So this is the shear rate, and this is the divergence simulated by the model. So the divergence, it's important because if it's red, it means that you are opening the ice, so you are forming leads, and when it's blue, you are closing leads or forming ridges. So having the right divergence, it's very important to simulate the sea ice state. So now I'm coming to the last part of the talk. So it's important with the divergence because it will open leads in the model output. And those leads can be observed from in situ, but they can also be observed from space. At least the largest one can be observed from space. So this is an animation where you see the lead fraction. So everywhere it's white, it means that you detect a lead. So we see many leads in Beaufort Sea, also many leads in Fram Strait. And what is nice with the model is that we reproduce relatively well this dynamics with leads opening very quickly and being closed either by the thermodynamics or just by the dynamical closing. So when we couple that, or when we will couple that to an atmosphere model and an ocean model, what we want to study is the impact on the heat fluxes. And this is a small example where we just compute the heat fluxes with bulk formula. So it's the simplest formula that are based on the sea ice concentration and thickness. And here it's an example where we open a lead, so the concentration drops. Then we close a bit the lead dynamically, and then we close it thermodynamically by forming new ice. And what is interesting to see is that the heat fluxes are much larger while the lead is still open. So that's all for today. The conclusion are that ice pack dynamics are complex but important to simulate. It's possible to simulate them with a sea ice model running at a reasonable cost and resolution. And there are potentially large impacts when you couple this new physics to an ocean model or to an atmosphere model. So thank you for your attention. I'm open to questions.
Thank you for this great talk.